Hello everyone, we are team Super Autonomous Ultra Instinct. I am Sumit Rakhoji.
I'm Most.
I'm sorry.
Our topic is traffic sign detection and planning. For the safe operation of an autonomous vehicle, it is critical for it to detect and classify the road signs. So we are simulating the environment in Gazebo, and we are testing our performance on the frames from the simulation. So for this, we are actually doing this in three parts. We are detecting the sign, we are classifying it according to the, and we are taking a plan according to the classifications.
So the model that we use here is Resonant 50, and kind of a breakdown of how it works is we get a 3-channel image. That just means RGB. We're getting it, and the first few layers try and extract the features from this image, and then the next few layers kind of propose the region of interest in the image. And the end of our model is going to be doing the bounding box and classification, the actual decision-making process. So to make our model work well, we had to do a lot of data augmentation. To make things work well, for it to understand simulated images well, we had to actually kind of farm our own data set. And what we did is we didn't farm that many images, but we did do a lot of data augmentation to make our lives easier, and that includes scaling, cropping, flipping, rotation, translation, brightness, contrast, saturation, and hue, and changing all of these in each image. Yeah, actually, wait, do you want to go back for 1 second? One key mention here is that some signs are flip variant, meaning that if you flip the image, the signs they will look different, and we had to take that into account when doing the data augmentation. So the training procedure is broken down as follows. We have 2 data sets, one that is real life images and our farm data set from the simulation. The way we train for the normal real life images is we would train them for 5 epochs with a frozen feature extractor, which is those earlier layers. And then we would train the feature extraction and the heads for 50 epochs together. And that was for real images. And then for the simulated images, we would fine tune the heads for 5 epochs and then train the feature extractor and the heads for 20 epochs after that.
So we trained 3 different models to show the process across different architectures. Our first was a generic Resonant 50. We then also trained the Resonant 50, adding in a training procedure with augmentations and also freezing and unfreezing the backbone. And we also trained a mobile net variant that was going to get us faster inference times, albeit at the cost of lower performance. We've broken down the results in terms of mean IOU, accuracy, and inference time. Mean IOU quantifies how well the detection is taking place. Accuracy quantifies how well the classification is taking place. And inference time is key because we're running in a real-world scenario. Resonant 50, with our augmentations and warm-up, exhibits significant increases over Resonant 50 baseline, which are noticeable in the performance of our model, even in simulation. MobileNet was also pretty performant and much faster, but we decided to stick in our demonstration with Resonant 50 in order to take advantage of the full accuracy and detection capabilities. We have 3 different planning and control setups depending on what sign is being detected. For stops, we just stop when the stop sign is big enough, and that is a proxy for how far away we are from the stop sign, when you should be heating it versus just seeing it in the distance and should continue to approach before stopping. After a while, we reset and keep going straight. For speed limits, when the size is appropriate again, that kind of quantifies that you're almost there and you're crossing it. So now we set a new speed threshold based on our controller, our input to the Acronym controller. For keep left, keep right, the process is a little bit more complicated because we want to be keeping left, keeping right for a while with our controller, but then we want to return the control back to the original controller after we've kept left or kept right for a few iterations. We have a few videos demonstrating the performance of our model. The first shows the performance of our model under various speed limits. So here, what we have is our model approaching speed limit in the distance. While we're in the distance, we can see on the right-hand panel that the live view and the frame that is doing inference on the left view. We can see that in the distance, it can't see the stop sign very well, but now it's seeing 100 and it's taking up a lot of speed. and it's zooming towards the next stop sign. Now it's seen the 30 and it has slowed down to an almost crawl. And that is the performance of our model on speed limits. On stop signs, you can see a similar performance that as we approach it in the distance, you can't tell that it's a stop sign with sufficient confidence. At some point now, it sees that it's a stop sign, it's very confident, but it's still too small for it to actually stop. So only as you get very close to the stop sign has it decided to stop. For keep left and keep right, a similar story happens. So it sees the keep left sign and it starts keeping left. You can notice the yellow line shows is moving toward the center of the screen because it's moving to the left. And now it sees the keep right sign and it starts slowly keeping right as it approaches it. So now you can see that this vehicle is keeping to the right. After a while, the original vehicle controller regains control. So in terms of our personal segment for this class, I would say that this class is very interesting. It was a very high level survey class, which was good for someone who doesn't have a lot of background, though I think some areas could have been explored more in terms of the planning and the state estimation. Sumit?
So
I can go
Yeah.
first. So some of the things that I enjoyed about the class was I'd never interfaced with ROS before for like real like robotic situations. And actually taking some of these machine learning models and implementing them in a pseudo real environment where, you know, we have to do something with our inferences. I have never been in a situation like that before, and that was kind of a good experience for me. Yeah, overall, I think the mathematics as well that we went into in class was interesting and gave some good background. I really appreciated that.
yeah, so I was someone who was really interested in autonomous vehicle. So this course is really good for me because it introduced me to the various aspects of the autonomous vehicles, and I'll particularly specifically learn the ROS, how to create the URDF files, SDF files, how to create the models. Yeah, so this class has been really a learning curve for me.
Thank you very much, and I hope you enjoyed our project in video.